Millions of years ago, Saturn has an extra moon. Perhaps 400 kilometers across and formed almost entirely of ice. But this moon is doomed. It's orbiting just too close to resist the immense forces of Saturn's gravity.
The rings probably formed from an object that got too close to Saturn. There's this invisible boundary around Saturn called the Roche limit, and that's the limit, depending on what you're made of, where Saturn's gravity is strong enough it will actually pull you apart, that the gravity on the side closer to Saturn is strong enough that, compared to the gravity on the other side, that will literally rip you apart. You don't have enough gravity of your own to stay together.
A leading theory suggests that just beyond Saturn's atmosphere, an ice moon approaches close to or even just inside its Roche limit. As Saturn's immense gravitational force pulls it apart, the moon begins to rupture catastrophically. A world ripped apart by its proximity to a giant. Up to 17,000 trillion tons of ice breaks apart in orbit around Saturn. And thanks to the speeds this material is traveling, it's likely that in just a few days, it spreads out to encircle the great giant. Saturn's iconic ring is now in place. But as Cassini turns its instruments towards it, it sees a single ring, transformed.
The images we returned, they were phenomenal. They were resolution a factor of maybe 20 times better than anything we had had before.
Cassini reveals how Saturn's giant rings have evolved. This debris now forms a disk wider than Jupiter, yet on average, just 10 meters thick. Within, moon-sized chunks of ice orbit the structure, clearing great voids, turning one ring into many. But it's as Cassini captures images with the sun directly above the equator that the most surprising feature of the rings emerges.
We knew this was going to be a time for us to investigate the third dimension, something that you don't get to see when you just look at a picture of Saturn's rings. And what we found was staggering. Just right out of the gate, we saw vertical structures. I just can't tell you how surprised we were to see this. It's just the spectacle of it was just unanticipated. I have just imagined flying along in a shuttlecraft across the ring, right, close to the ring. So to my perspective, it would be almost like it was an infinite sheet of gleaming debris. And I'm flying along and flying along and flying along, and suddenly I come upon a wall of rubble that's 2 miles high. I mean, is that cool or what? Really, I've said over and over again, they should put that in a movie.
This once tiny world of rock and ice that has seen the most dramatic transformations is today the solar system's greatest jewel. After more than a decade in orbit, Cassini has forever deepened our understanding of Saturn. But its mission is far from over.
The Earth is speeding up. It's literally spinning faster. Could it cause a tech meltdown? And what have melting glaciers got to do with it? You may or may not know, I mean, I wouldn't expect you to know, there are 86,160 seconds in a day. But scientists who measure time have found that in 2021, the average day is 0.05 milliseconds less than this. That's because the Earth is literally speeding up. Okay, so you might think 0.05 milliseconds, so what? But this actually goes against everything that we expect to see happen, and scientists are desperately trying to find an answer. Because since its creation, Earth's spin has actually been getting slower. In a not very recent history, the days on Earth used to be twice as fast. But what does a faster spinning Earth actually mean? 3.5 billion years ago, the planet's rotation used to be only 12 hours long. At that kind of pace, life would really suck. We'd have nightmarish weather patterns, with hurricanes tearing across the land. Centrifugal force would pull water towards the equator, flooding entire regions like Indonesia and the northern tip of South America. Okay, that's a worst case scenario, and Earth is unlikely to ever spin that fast again. But if we keep speeding up, it could be bad in another way. By 2030, there could be a full-scale technological meltdown. GPS relies on precision timing, and if a day falls too far behind that 24-hour benchmark, there could be disastrous consequences. For one, satellites could lose their correct place in the atmosphere, and we'd lose all means of being able to predict where they are in the sky. If we leave this slip for too long without correcting it, then our navigation systems will be completely wrong, throwing all of our smart technology off course. Fortunately for us, we can sidestep this disaster, and there's a fairly easy workaround. Timekeepers can add and take away what's known as leap seconds to account for these tiny differences. They can alter what's known as international atomic time, which can be adjusted for the subtle discrepancies between the Earth's rotation and our clocks. And what's pretty mind-blowing is that by observing the night sky, we can keep track of these tiny changes. So keeping time is a pretty skilled art form. That's how we know that the Earth is spinning faster. But that doesn't explain why, despite billions of years of slowing down, the Earth's rotation is speeding up. So what's causing it? This is Dr. Jazz Hill-Valler. She's an expert in how the climate affects the Earth's rotation.
So we probably all know that the melting ice caps is going to cause sea levels to rise. Well, it's also causing the Earth to spin faster. And what happens when the Earth spins faster is that we get a greater centrifugal force. Imagine a figure skater. When you watch figure skaters, they start off spinning really slow with their arms out, and as they bring their arms in, they start to turn faster and faster. That's because they're bringing more mass towards the center of their rotation. So how can that happen on the Earth? Well, water has this crazy property where when it freezes, it actually expands. So if you think about all of the glaciers and the mountains and the ice sheets as being these huge, tall, towering sheets of ice, well, what would happen if we suddenly melted them really quickly, which is something that we're seeing happening at the moment? If we take all of that mass in those glaciers and those ice sheets and suddenly it melts and gets closer and closer to the surface, just like the figure skater bringing their arms in, all of that mass is going towards the center of rotation, meaning that the Earth is going to start spinning faster.
This meltwater currently sits at the poles. This is why right now scientists believe the Earth is spinning faster than usual. So will it get faster forever? Here's the conundrum. Actually, scientists expect this to be just a blip. Although it's been getting faster for the last 2 years, experts expect the Earth to go back to its longer-term pattern of slowing down. And it's the Moon that's causing this.
This is to do with the tidal relationship between the Moon and the Earth. We only see one face of the Moon. It's tidally locked with the Earth. So as the Earth is turning, the Moon is pulling the ocean towards it, and then as we move away, the oceans go back round, and that causes our tides. So this kind of wobbly dance between the Moon and the Earth means that the Moon is slowing down the Earth, and all that energy that's lost from the Earth slowing in its rotation is getting put into the Moon's orbit, and the Moon is actually moving further away.
As it continues to drift away, the effect of the Moon's gravity on Earth weakens, causing us in the longer term to slow down. What's more, over time, the melted water in the polar regions could actually make the Earth spin slower. Some scientists believe that the water will drift towards the equator, which will further slow down the Earth's rotation. This is called equatorial bulging. Think of it as a big spare tyre around the middle of the Earth. It exists already down to the centrifugal force exerted on the ocean by Earth's rotation. But adding to the weight of this tyre is no good thing.
All of that excess water is going to go and sit around the equator, which means that there's more mass further out from the centre of rotation. The equatorial bulge of water is going to get higher, which means that around the equator there's going to be even higher sea levels than we originally predicted. It could mean that hurricanes and typhoons and cyclones that form at the equator could become more severe because there's more water vapor there. So the increased severity of these storms because of the Earth spinning faster is probably only going to be a temporary effect, but that doesn't mean we shouldn't be worried about it, because more severe storms means that we're going to see more severe natural disasters happening all over the planet.
So although at first glance it doesn't seem that important that the Earth is spinning a bit faster, it really does matter, because it could be a big hint as to what else the climate crisis has in store.
We lost comm with the spacecraft.
If the spacecraft wasn't back up and running by the time we flew past Pluto, our 9-year wait would have been for nothing.
There's a little bit of drama because this is true exploration. New Horizons is flying into the unknown.
When we got there, we saw something that absolutely blew our minds. It was incredible. When we saw these photographs of what it actually looked like, really a world in its own right, it was mind-blowing. There was active geology on Pluto right now. Something so far from the sun should just be a cold, dead world, but it's not. It had this living, breathing heart.
3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft in a decade.
We've been using the best telescopes that we had available to us to observe it for years, most notably the Hubble Space Telescope. And through a lot of observations, a map was made of Pluto's brightness, but it was very fuzzy. You have some light periods, some dark bits, but that's all we had. The Voyager spacecrafts that explored the rest of the solar system didn't go past Pluto. We had to send a dedicated spacecraft to go and have a look at Pluto because we'd never seen it before. I mean, lots of people move their personal life around their work, and mine's no different, but it is different in the sense that, you know, the spacecraft goes past Pluto once in your lifetime. And so we arranged our wedding ahead of that, and then we actually decided to wait to have children until after Pluto. When you have a mission like Pluto, you have times where you really are quite busy on the mission. You're taking new data. We flew past Jupiter, that gives you data. We're looking at the stars to make sure our instruments are still operating and they're healthy. But there are periods whereby, you know, the spacecraft is in hibernation, it's spinning, it's not taking data. If there's a problem, it knows how to call us, but other than that, it's just marching forward towards Pluto.
We lost comm with the spacecraft. Totally silent. And so you can imagine when you're in any kind of critical situation, the worst thing is lack of any information. And that's essentially what we had.
Pluto Ace, Mom, on New Horizons Pluto 1. Could you advise why we are not locking up to telemetry?
About the 4th of July, so American Independence Day in 2015, it goes into safe mode. It just stops doing anything except pointing back to the Earth and telling us there's a problem.
Mom, Pluto Ace, stand by. I'll check with the station on the status of telemetry.
So to put that into context, our encounter is 10 days at this point out, and it's a flyby. We're going to go past Pluto once. We're not going to slow down. We're not going to stop. We're not entering the system. We're flying by it. If the spacecraft wasn't back up and running by the time we flew past Pluto, our 9-year wait would have been for nothing.
Station 4-3, Pluto Ace.
Mom, on New Horizons Pluto 1. Go ahead, Pluto Ace.
We found the spacecraft. It was responding to us. It was giving us information, but it was in a state that could not accomplish the encounter with Pluto.
It takes 9 hours to talk to the spacecraft at that point. And so we were doing the tests on the ground, making sure that the sequence that we were going to upload was working.
It took us 3 days to do that. Around the clock, we slept in our offices. No one wanted to leave because we had waited all this time, and there was no way that we were going to let this opportunity slip by.
And it will transmit a message back to the Earth for about 20 minutes, in which we'll find out how it's doing. But there's a little bit of drama because this is true exploration. New Horizons is flying into the unknown.
So before we entered the Pluto system, we downloaded the highest spatial resolution observations we'd made to date. So there's only 5 of us in the whole world that had seen this image of Pluto.
Oh, my hair looks better like that.
And we're all just sitting there at that moment of like, whoa.
We've recorded data of the Pluto system, and we're outbound for Pluto.
To see that was just incredible. It was a life-changing experience.
Look what we accomplished. It's truly amazing. Humankind can go out and explore these worlds. And to see Pluto be revealed just before our eyes.
So when you see an image of a new world, especially one as diverse as Pluto, there are so many things you can take home from it. And one of the first that jumped out of me is that heart-shaped region that's in the middle of the encounter hemisphere. And in particular on the left-hand side of the heart, it's very smooth. And you don't get smooth regions on any worlds unless there's some form of active reprocessing. And so there was active geology on Pluto right now. Couldn't believe it. Still can't really. So why is it so geologically active? We still don't have all the answers. Does Pluto have a subsurface ocean? There was mountains with holes in, which points to the idea of a volcano. Maybe it's a cryovolcano, a volcano that erupts ice. And that would be better explained if there was enough heating to sort of maintain a liquid water ocean. Pluto's really cold. really, really, really cold, colder than you could possibly imagine cold. It's so cold that water there is sort of the bedrock. The ice is so hard it can form mountains, which is something that of course just couldn't occur on the Earth. And so on Pluto we see these big ice structures. So it all kind of implies that there's lots on Pluto that is quite fresh and new. And so whether you could have life that is in a sort of this contained place, subsurface, so dark, but with an energy source, it's hard to imagine from what we know of life. It's not impossible, but it's going to be a difficult thing to get to see because it's so far from the Earth. We don't want to do any harm. You certainly wouldn't want to send, a probe into this pristine world because you could kill everything that was in there just as you discover it. So it's definitely the thing of sci-fi, and it's fun to think about, but it's going to be a really difficult thing to test. Anyone that's been working at home during this lockdown will understand the frustration of limited broadband. And we have this on New Horizons because the spacecraft is so far from the Earth. Getting a signal back is so weak. It's meant that our 6 gigabytes of data that the spacecraft took during the encounter is still being downloaded. You're really trying to make sure you have everything on the ground before it gets wiped from the spacecraft, before it's gone from humanity forever. You want to make sure you have everything. True exploration isn't something that normal people get to do, right? I've got to explore worlds that have never been seen before. And I think once you've had that taste, it's just, you can't let it go. It's not quite adrenaline junkie stuff, but you want to do it again. And so it would be absolutely incredible to do it twice in a lifetime. What a privilege.
Black holes aren't what you think they are. They're not holes, they're not black, and we can actually see them. And we've even managed to take a picture of one. You are currently looking at something incredible. The first ever image of a black hole, the one at the center of the Messier 87 galaxy, 55 million light years away. Now we know there's a black hole at the center of our galaxy, the Milky Way, which is 27,000 light years from the solar system. And we know that it's super massive because in 2008, Professor Andrea Getz and her team measured how big it was and found that it was 4 million times more massive than the Sun. This measurement was such a big deal that in 2020, she won the Nobel Prize in Physics. To work this out, they studied the orbits of the stars moving at incredible speeds around the black hole and used this to weigh the black hole.
If there's a black hole at the center of our galaxy, that's going to force these objects that are really close to the black hole to move much faster than they would move if there were no black hole. So the first thing you want to see is that there are very fast-moving objects where you think the black hole is. If there's a black hole, there's a further prediction you can make about what these stars are going to do. They're going to move around the black hole on very short periods. In other words, you're going to be able to see them move on more than just straight lines. As part of their travel around the black hole, these stars are going to move around the black hole because of the gravity, just like planets move around the sun.
Contrary to their name and to common belief, not all black holes are black. In fact, the gas and dust that spirals around the black hole can be accelerated to huge speeds, which heats up due to friction, causing it to glow. In fact, feeding black holes are some of the brightest objects in the entire universe. There's a supermassive black hole in the center of every galaxy. So how do we know? When quasars were first discovered, they were thought to be hugely bright stars, and any ideas of them being black holes were dismissed as just crazy. But we now know they are feeding black holes. And they're described as feeding because stars and gas clouds that get too close are torn apart violently by the immense gravity and then lost beyond the event horizon to become part of the black hole. They're essentially like a little snack for the black hole. There's a quasar at the center of the Cygnus A galaxy that's 1 trillion times brighter than our sun. And Dr. Andy Fabian from the University of Cambridge is studying this quasar with X-ray images. These help reveal the gas clouds that are orbiting around the black hole.
There's a lot of other things going on out there, and enormous amounts of energy being released, which we can only be aware of if we look with X-ray eyes. We could see what was going on at the center, and we could start to understand how the black hole was feeding energy out into all the surrounding gas.
The friction generated by this dense atmosphere of gases produces the hottest and most electrically charged environment in the universe.
What we know is that the hotter something gets, the brighter it gets, the more light it emits.
By feeding on all this gas, the black holes sometimes end up with just too much material around them and end up burping out a load of it, which then impacts the galaxy. This can actually expel a load of the gas that the galaxy would have used to make more stars, and essentially stopping the galaxy from growing any bigger. So black holes seem to wield a worrying amount of power. They can literally control how big a galaxy can grow.
Galaxies could, in a way, be much bigger than they currently are. Something is stopping them growing larger, and that something is the black hole at the center. Now, this is bizarre because the ratio of the size of the black hole to the size of the galaxy is the same as the ratio between a grape, or something this big, and the size of the Earth.
It sounds impossible that something that small would have so much control over something that big, but that is what's going on. It's been calculated that the mass of a black hole is on average about 0.5% of the mass of a galaxy. Essentially, the bigger the galaxy, the bigger the black hole will be. This correlation made astronomers start to wonder whether black holes might have been present or even responsible for the birth of their galaxy.
Because it really meant that there was something linking these tiny supermassive black holes in the center of galaxies with the whole galaxy itself. It meant that somehow their whole history had been intertwined, that the growth of the galaxies and the growth of the black holes was somehow related.
Now, in the early universe, we don't know if stars formed first or if black holes formed first. But if the black hole formed first, then the galaxy of stars could have then formed out of the gas that was swirling around it. What everyone really wants to know, though, is what happens when a star gets swallowed by a black hole. Well, a couple of years ago, a gas cloud called G2 came perilously close to the event horizon of the black hole at the center of our galaxy, the Milky Way.
This is the first time, really in human history, that we have not only known an event like this was going to happen, but that we are prepared with the right sort of technology to see the details unfold.
Astronomers monitoring the event were able to test the effects of the black hole on this gas cloud. It was essentially on a collision course with one of the most powerful entities in the entire universe, and it was being stretched out on its way there.
It was moving quite fast, and it's not moving in a straight line, but it's a curved line. And that's a very, very bad sign, because it tells you, well, there's something acting on it. It tells you, wow, gravity is pulling on that object.
Instead, though, it was spaghettified, and it circulated the black hole and then was essentially catapulted back out into space. Lucky escape for the gas cloud. This event confirmed that it is possible to get perilously close to a black hole and still escape. So, there's a black hole at the center of every galaxy, and they have the power to dominate everything around them. But they're not just giant hoovers sucking everything up around them. Stars, gas, dust, they're all happy to orbit them with no issues.
We're seeing the black hole at the center having a galaxy-wide effect on the surroundings.
So if they really do have a galaxy-wide stronghold, and the one at the center of the Milky Way has been there since its existence, that means that you, me, and all the stars that we can see have always, and are currently, right now, orbiting a supermassive black hole.
This is one of the few places in our solar system where we have a good chance to look for life. There's evidence for a vast subsurface ocean below the icy crust of the Moon. The amount of water that's suspected there is many times more than all oceans together we have on Earth. On the poles, you're approaching minus 200 degrees Celsius. Icicles that could be several meters high might be present. And if you're very lucky, then you might just spot a plume erupting nearby, like an ice volcano that ejects material from the subsurface to enormous altitudes. On top of that, there's a good chance that there's an energy source at the bottom of the ocean, hydrothermal activity, that can support the emergence of life. That makes Europa outstanding. Europa Clipper is the first mission that goes to the outer solar system that has the exclusive goal to investigate the habitability of a body in the outer solar system. It will launch in October 24 and will arrive at Jupiter in April 2030, so it's 5.5 years for Europa Clipper. Jupiter has like about 70 moons, so the number increases like every year by a bit. But there are 4 moons that stand out, that are the so-called Galilean moons. The innermost is Io, then Europa, then Ganymede, and then Callisto. With the telescopic observations before the arrival of the first spacecraft, you could see that some of these moons are really, really bright. They reflect way more light than a rocky surface would. And so, for example, Europa and also Enceladus, they are one of the brightest objects. And so it was suspected already at that time that the surface might be composed of shiny, reflecting water ice. I mean, after the investigations of the Galileo spacecraft in the late 90s, Europa became a prime target in planetary science all over the solar system. Because with a huge subsurface ocean, with the spectral hydrothermal activity, that became the first place that could be habitable in our solar system besides maybe Mars. That immediately sparked proposals of missions to go back to Jupiter and specifically investigate Europa. I mean, if you are a planetary scientist, probably the most rewarding science goal is to see if a planetary body is habitable or actually inhabited. So Europa Clipper will stay in orbit around Jupiter, and in most of its revolutions, it will have a close flyby at Europa. And the flybys are arranged in a way that it's like a web in the end surrounding the moon, that you have in the end a good overview over almost the entire surface after these 50 flybys. During this close flybys, you get an idea of what is evaporating from the surface of Europa. And from that, of course, you learn about the makeup, the composition of the surface. And this is, of course, specifically true if there's plume and venting activity. That's what I really would put a smile on my face, if we could measure plume material that's connected to the subsurface ocean of Europa. The instrument called SUDA, the Surface Dust Analyzer, is the instrument I'm working on. It measures the composition of tiny grains that are surrounding Europa, mostly ice grains. And these grains are knocked off the surface by micrometeorite impacts. With the SUDA instrument, we can sample these materials, and with that we get an idea about the surface composition. We could constrain what salts were there in the ocean, if there's an alkaline, neutral, or basic environment, if there's hydrothermal activity at the bottom of the ocean, what the organic chemistry inside the ocean has evolved to. Unfortunately, we currently only have one example of a planetary body or a moon where life exists. And so it's very difficult to speculate about the nature of life elsewhere. If we look for signs of life on an icy moon like Europa, it's probably the most straightforward to just look for simple forms of life. If there would be complex civilizations in these subsurface oceans, we probably would have known by now, right? But I know that at least for the life on Earth, the access to oxygen is important to develop complex life compared to simple monocellular life. So this is one of the big science questions that Europa Clipper wants to answer. Has the Europa Ocean access to oxygen that is created on the surface? So is material from the surface cycling back down to the ocean? If yes, then oxygen might be available in the ocean, and this opens up the possibility for more complex life. And not just a single cell, but maybe fish-like complex life. Everything between one cell or no life or fish-like life, like complex organisms that might be even intelligent or not, nobody knows. It's really up in the air. I look very much forward to the launch. It will be launched on a Falcon Heavy that was decided only a few months ago. So one of Elon Musk's rockets. And I'm really much looking forward because I never saw a rocket launch in my life. I'd like to see it. But on the other hand, it'll make me nervous. So that's always a problem. If rockets have a chance, even the safest rockets have a chance of like a 1% or 2% that there's some failure, and then everything was in vain. Because all the development has been done. Most instruments have been crafted twice, that you have a spare. So I really hope that the launch will go well. So I think it's one of the most exciting missions there is, and I'm really glad that I can participate in these endeavors.
So humans are going to Mars, and soon, lots of them. SpaceX could be going as soon as 2026, NASA and China by the 2030s, and India, Russia and the United Arab Emirates are all planning on it too. But what happens when they all get there? How can we actually survive? Well, some lucky scientists have already been there. Okay, not really. They're living in a Mars simulation right here on Earth to troubleshoot what could go catastrophically wrong when they do go to Mars. It's time to explore the unexplored. Okay, let's break this down into two key challenges we're going to need to overcome if we go to Mars: the physical and the psychological. Let's start with the physical. In many ways, Mars and Earth are quite alike. It has a similar dry landmass, volcanoes, craters, and its days are just 37 minutes longer than ours. What would you do with an extra 37 minutes? But that is where the similarities end, and it's the differences where the problems start. Gravity is just 38% of that on Earth. It means that you can jump higher, but you'll lose muscle mass. Imagine Dwayne "The Rock" Johnson training his chest every day with an 100-kilo bench press to maintain that impeccable physique. Suddenly, you land on Mars, and all that's available is a 38-kilo weight. Over time, his chest is going to get weaker and weaker. And it's a similar situation for astronauts going to Mars. Then there's the atmosphere, which is incredibly toxic. It's around 95% carbon dioxide. And to make matters worse, Mars is bombarded with radiation. And you get the idea. Mars is extremely dangerous. But luckily, there's a team of scientists who are actively trying to resolve these problems before we get there.
So when we talk about Mars simulations, what we're doing is we are trying to mimic the surface phase of a human robotic Mars mission. There's a million things that can go wrong. So when we think about Mars, we're talking about a world that is up to 380 million kilometers away from the Earth, which happens to be about 1,000 times the distance to the moon. And so it's probably 1,000 times more things that can go wrong. What we learned through our missions, it's not only the big things that are challenging, it's the small things. Think of being in the spacesuit. Despite the air condition, you start to sweat, but you cannot scratch your nose in the helmet, obviously. So little things like a little piece of foam where I can simply rub your nose into it and make sure you don't sneeze inside the helmet, which is a very bad idea, by the way, is a little thing that doesn't sound very glorious, but it's the things that make your work easier. And really making sure that you have gone through the ins and outs of those little details can be a game changer. We have been doing those Mars simulations for 13 campaigns now, since almost 20 years now. And there's literally hundreds of experiments we did, and many of them went wrong or did not turn out the way like we expected them to do. And so we live and breathe the mantra of fail fast, fail cheap, and have a steep learning curve, because that's where you get better. We died many deaths, simulated, of course.
So gravity, atmosphere, and radiation are not actually the main concerns. These are the big things that we already know about, that we can create technology to help mitigate them. It's the small things that we don't know about yet. They're what could kill you, and there's a lot of them. So far, the answer to most of the physical challenges has been better technology and better spacesuits. But physical survival is only part of the battle. The team are also pioneering incredibly advanced psychological studies to figure out who will be the best humans to go to Mars.
We think that there's no such thing as a born astronaut. When we select analog astronauts for the Austrian Space Forum, this has been done very, very carefully. It's a multi-month process. We're evaluating, we just did a recent count from the last class, 637 individual parameters, anything from your cholesterol level to the length of your pinky finger and your ability to entertain little children and psychological factors and so on. You're much more looking for team players who are outstanding when it comes to health, but they also have technical competence, but at the same time who are also to display social warmth. They know how to tell a joke in the airlock at the right time. They know how to cook. They know how to do a magic trick. They can play the guitar. They can also settle down a broken leg or so. We are not looking into psychological clones of each other, but they need to complement each other. And so we're looking, actually from the anthropometric point of view, we're looking for the average Joe, the average Jane.
Or an average Josie?
So we have people who, in the beginning, who have a high technical competence, but then the work doesn't stop here, because you need to continuously monitoring the activities throughout the mission. That's exactly what we're doing with our simulations. For instance, we are in a previous experiment in 2018 in Oman, we had an artificial intelligence machine learning algorithm actually, who was looking into the pitch of the voices when people talk to each other. And we know when people are under stress, the average pitch shifts just slightly above the average. Or for this mission in Israel right now, we had one of the experiments, was a fantastic experiment. The astronauts would have locators, so we could produce heat maps where the astronauts would congregate throughout the mission, or also relative heat maps, how much physical spacing they have in between them. If you don't like somebody, you tend to increase the distance, for instance. And so we're looking at the methods that tell us, here's a stressful situation emerging before the people would realize it. And magically, then everything goes according to plan. And so it's about keeping them functional, by keeping them happy, by feeding them well, no food, no fight. But also making sure they don't smash each other's heads before leaving the lunar orbit.
So, with the right training, technological development, and people management, Dr. Gromer believes that we can definitely survive on Mars. But so far, we've only been focusing on a finite scientific mission. Go, survive for a bit, and then return. And that's understandable, given how many risks there are for even doing that. But this hasn't stopped people from dreaming even bigger. Elon Musk has famously said that we're going to Mars for good, to become a multi-planetary species. Some scientists have taken this and come up with some scary, speculative solutions to explain how we might survive. One of those is through mutations. The high levels of radiation on Mars could cause our bodies to change, and it's possible that some of these changes might actually help us survive. It's hard to predict how quickly this might take and the effects that it might have, but some scientists say that it could take just a few generations. Like, we could see changes in our skin tone to deal with the radiation. Could we go green? Our bone density might alter to account for the lack of gravity, and we might not even need our immune systems because we'll be living in such a sterile environment. But all of this is only relevant if we're actually going. Will we really ever be setting off to Mars for good?
Yes, we will. I can give you this in written. It's only a natural process. I think at the core of our beliefs and of our heart and our DNA, we are a migratory species. Our children and grandchildren will look up to the sky, to the moon, and see little dots of light out there on the lunar surface saying, we are out there. It's a statement to the universe. And the same will happen to Mars and the worlds beyond. It's just a matter of time.
The James Webb Space Telescope is revealing the universe like never before. Our planets, the furthest galaxies, and the strangest phenomena.
And what you can see is actually material falling into a black hole.
And that's only in the first few weeks. There's going to be a lot more discoveries to come.
The James Webb Space Telescope is a product of decades of hard work from scientists around the world.
I have been waiting my entire astronomy career for JWST. It is absolutely revolutionary compared to what was available.
It's very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy. And it just doesn't happen very often in the history of science, and that's really exciting and significant.
One of the things that makes James Webb so special is its gigantic mirror.
So that there are various things that make the primary mirror on James Webb special and incredible. I mean, the first is the sheer size of the mirror. It's the largest one ever launched.
The Webb mirror is around 6.5 meters in size. So if you can imagine that, that's bigger than most houses that you're walking by.
It's so large it wouldn't fit in the rocket, so they had to devise a way of folding it up so that it would fit inside the top of the rocket.
It's absolutely humongous. And that makes a really big difference in terms of the sensitivity of the telescope.
Well, it's thousands of times more sensitive than Hubble. It's a step forward of factors of 1,000 or more. Factors of several thousand, in fact. I'm correcting myself.
The bigger the mirror, the more light you collect. The bigger the collecting area, the more sensitive you are and the further you can see.
The other thing that makes it absolutely incredible is the precision with which it's been made. If the mirror was stretched to be the size of the United States and you were to measure the size of the biggest bumps and dips on the mirror, you're only looking at a bump or a dip of order 1 centimetre in size. It's absolutely incredible, and that's what generates the near-perfect images from the primary mirror.
But it's not just the mirror that makes the images from James Webb so incredible. It's also the type of light that it detects. The James Webb Space Telescope detects infrared light, which is a wavelength of light that we can't see. But the unique properties of infrared make it incredible for exploration.
So with the infrared light, you can see the atmospheres of exoplanets. There's molecules in star formation regions, things like caffeine and alcohol and water ice, the signatures of life around other planets.
So just a few things then. Infrared opens up the possibilities for astronomers like Olivia and allows them to capture images that would previously be impossible in the optical range. But even within the infrared spectrum, there are multiple different wavelengths. On board Webb, there are 3 instruments that observe near infrared. This is closer to the visible spectrum. But the instrument that's garnering the world's attention is the mid-infrared instrument on board JWST, known as MIRI.
MIRI is essential for JWST. Without it, you can't see the cooler phenomena in the universe. You can't peer back as into the earlier stages of star formation as you would like.
So MIRI is an incredibly significant and important instrument. The image contains far more detail than has ever been done before.
So when we look at it in a new wavelength of light, we find things that we hadn't expected to see, and that's a really important part of how you discover things about the universe.
MIRI allows us to see further along the infrared spectrum, and this in turn allows us to see through dust clouds and further back in time than ever before. That's because as galaxies move away from us, the colour they emit shifts further into the infrared, so the longer the wavelength we can observe, the further back in time we can see. But despite the capabilities of MIRI, it very nearly didn't make it on board James Webb.
So MIRI wasn't initially part of those plans because it seemed technically very complicated, and I think people were thinking about the science in a slightly different way. And so I started making the case that really we needed to add a mid-infrared facility to the telescope.
Gillian Wright is the European Principal Investigator for MIRI and the Director of the UK Astronomy Technology Centre, and was instrumental in pitching to get MIRI on board Webb.
When I found out it was confirmed that MIRI was going to be on board, I remember being very happy and also knowing that I was going to be very busy for a large number of years.
Gillian wasn't wrong. Construction of James Webb Space Telescope started in 2004, and 17 years of work later, on Christmas Day 2021, with MIRI securely on board, the telescope finally launched.
And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
I've been looking forward for the Webb launch for many, many years. And as it got closer to Christmas Day, I was extremely nervous. I don't think my family enjoyed Christmas morning with me because I had on the TV the Webb launch playing, and I was quite nervous. I had my pillows ready in case I needed to hide.
Everything went perfectly. It was an incredible launch. It was a pleasure to watch.
So it was a very good Christmas present.
It was a lovely Christmas present, it really was.
Over the next few months, the James Webb Space Telescope travelled over 1.5 million kilometres away from Earth to its new home, gradually turning on the instruments along the way.
So then it was getting really exciting because we've been from Christmas Day all the way through until the late spring when MIRI finally gets turned on.
As the instruments are being turned on, it's both exciting and it's nerve-wracking because you know that there could be things wrong.
After decades of work, the James Webb Space Telescope was finally operational, and it wasn't long before the images started coming in.
I knew when Webb was going to take its first images, they were going to be spectacular. What had not prepared me was just how spectacular they were going to be.
The first images were just incredible, just so beautiful. It was amazing.
And then when the first images came back, I was just absolutely astounded at how good everything performed. And I've been smiling ever since. It's almost emotional.
The images are spectacular. And the only thing more spectacular than the images are the discoveries that lie within them.
So one of the things I think that's really exciting about the early images is the way they show how MIRI really adds information.
I can see details in there that I knew existed, but I never thought I'd be able to see with a scientific instrument. Some of the first Webb images released were of the Southern Ring Nebula. This is a planetary nebula, which is a star at the very end of its life. In the MIRI image, we see actually a second star. So we can see a red star and a white star. So these are actually a binary system, and that's the very first time we've seen this binary companion in the Southern Ring Nebula. This is an image of Stephan's quintet, 5 galaxies that are interacting with each other. And what you can see in this galaxy up here is actually material falling into a black hole in an active galactic nuclei. You can see the material in the galaxy is actually orbiting and falling into the galaxy itself. This is 13 times further than what we've been able to see before in the infrared.
I mean, JWST has already found the furthest galaxies we've ever seen, the highest redshift ones, the closest, and that's only in the first few weeks of operation, and that's really exciting, and I think it's an indication that there's going to be a lot more discoveries to come.
With Webb, we've designed it to answer many of the questions we already know about the universe. But as with all new telescopes, there's a realm of new discoveries.
The mysteries that will arise, I think they're really exciting.
New questions to answer.
The questions we don't know how to ask just now, and I think that's really exciting to see something that not only has nobody ever seen it before, but nobody expected to see it.
I feel very privileged to be part of this.
I'm proud to be part of JWST. It's been an amazing journey and a fantastic privilege, really, to be part of it.
I think it's just incredible. I helped make that instrument, and when I see these images, I'm just full of smiles.
Scotland's Astronomer Royal, Catherine Haymans, believes observations of the universe don't agree on its age because the mathematical models aren't quite right. She suspects our understanding of the dark universe may be an illusion.
Our best information about the universe tells us what the universe looked like right after the Big Bang. And from that data, we can come up with a model of what the universe should look like today. But what we're finding is that the universe that we observe isn't quite what we expected And we can't fully explain the universe that we're observing today. It means that we can't trust it when it tells us how old our universe is. It just doesn't add up.
Catherine thinks that although researchers have calculated how much of the dark universe is out there, they've little real idea of its impact.
We know that the stuff we're made up of, the Earth, the Moon, the Sun, everything we can see in the universe, that accounts for less than 5% of it. The rest is dark. Two components, dark matter and dark energy. Dark matter, that's the kind of the big gravitational stuff that keeps everything bound in our universe together. And then, its evil twin, dark energy, which appears to be causing the expansion of our universe to accelerate. Those are our three main ingredients, and we only understand 5% of it. So you could picture this as an epic fail for science. We don't understand 95% of our universe, but I like to think of this as a big challenge, because if we can understand that, then hopefully that will really revolutionise our understanding of everything around us.
To try and work out just how dark matter impacts the universe, Catherine investigates how it has evolved over time since the Big Bang.
So this is a map of dark matter spanning across the sky, where you can see bright spots. That's where there's lots and lots of dark matter, and as the colour gets darker, that's where there's emptier voids, where there's much less dark matter in our universe. And what we're finding is not what we were expecting. We can see clumps, we can see voids, we can see that cosmic web-like structure, but it's not exactly what we expected. It's a lot smoother than predicted for what we should see today. That's a bit of a problem, because it takes time for these dark matter structures to form.
Catherine has spent decades fine-tuning and finessing her dark matter map.
So for about the last 20 years, I've been working to map out the invisible dark matter in our universe. This is our map of the north. We've got another map of the south. And whilst this is one of the largest dark matter maps that we've ever been able to make, it's still quite a small patch of the sky. So we might have been unlucky. This might have been just a weird patch of the universe that we've looked at, but it's not exactly what we expected. And the fact that this is a lot smoother suggests that the universe is slightly younger than we first thought.
As yet, Catherine is unsure just how much younger. But her work continues.
Sent to look for conditions where life could have begun is NASA's Mars Reconnaissance Orbiter. MRO sends back more data than all other Mars missions combined.
MRO has 3 cameras on board. The first is the Marcy weather camera. It sees horizon to horizon on every orbit. So it builds up a map of the entire planet every day, so you can see a global weather map every day on Mars. The second camera is the context camera. It provides high resolution, and it's covered about 99% of the surface.
MRO has made more than 60,000 orbits. Its high-resolution cameras revealing Mars in unprecedented detail, discovering polar avalanches, shifting sand dunes, and what look like seasonal flows of sand or even liquid meltwater. Then, in 2017, MRO turns its gaze to one of the red planet's oldest features, the Eridania Basin, thought to have been an ancient sea.
Eridania Basin is a huge basin in some of the most ancient crust on Mars. It formed about 3.8 billion years ago, and it held more water than 10 times that of the Great Lakes, or 3 times that of the Caspian Sea on Earth.
And it is on the ancient seabed that MRO sees something remarkable.
MRO saw a massive 400-meter thick deposit formed from a mineral that forms in deep-sea hydrothermal environments, such as one that might have undersea vents.
Mars not only had the same ingredients for life as Earth, it also had an active environment to spark it into action.
Eridania Basin was an ancient sea 3.7 to 3.8 billion years ago, and that's about the same time when life was first emerging on Earth. This might have been a place where life could have existed, because those hydrothermal vents underneath that sea might have created a very conducive environment for life.
These initial conditions in the history of both planets look so similar that it seems reasonable to expect that this could eventually lead to life.
These actively fertile conditions are thought to survive in places like the Eridania Basin for hundreds of millions of years. But then, 3.7 billion years ago, something happens that transforms prospects for life on Mars forever.
Mars underwent a fairly substantial transformation in its climate. The climate got colder. What liquid water there was either soaked into the ground and froze or froze at the surface. A lot of it ultimately would get transported to the poles, where it forms these big, thick ice caps that we see today.
At the same time as the temperature plummets, Mars becomes more volcanically active, leading to catastrophic flooding. Water rages down from the southern highlands until, in a place known as Ekis Chasma, it plunges over cliffs 4 kilometers high. Creating the largest waterfall the solar system has ever seen. Cascading into a spectacular canyon 10 kilometers wide by 100 kilometers long. Once the floods subside, the water disappears. The only trace it ever existed etched into the planet's surface.
The strongest magnet in the universe has been discovered. It's an exotic, ultra-rare neutron star. It's called GROJ 1008-57, and it's got a magnetic field over 1 trillion times stronger than the Earth's. Stars like this are so strong that they have the power to do ridiculous things to anything that comes even remotely close. If you got within 1,000 kilometers of it, you'd simply dissolve. Your atoms would be super stretched. Their shape would warp into something completely unrecognizable. The molecular structure that makes you up, forget about it, it's gone. You'd just disappear. So nothing good can come from messing with a star like this. But how magnetic is it? Well, its field is calculated to be 1 billion Tesla. Tesla is the unit we use to measure how magnetic something is. Just to put this into context, the Earth's magnetic field is a millionth of a Tesla, but we've cooked up something far stronger in the lab. This is what 1200 Tesla did. Despite its supercharged magnetic strength, the star is actually incredibly small. It has a diameter of 20 kilometers. You might be wondering just what makes a star like this so magnetic? First, we need to find out more about how these neutron stars and their rarer subtypes come about. Neutron stars are created by the death of massive stars. Having run out of fuel, their upper layers are obliterated and the core collapses. We witness an extreme explosion, a supernova. Left over electrons and protons come together to form neutrons, and with the right solar mass, we end up with a neutron star, a severely squashed down version of what was there before. Astronomically speaking, they're the densest thing out there.
If you dropped a marshmallow onto a neutron star, it would have the energy of an atomic bomb because the gravity is so powerful.
So they're cosmically very small, but unbelievably dense. Let's put it another way. If I had a matchbox full of neutron star material, it would weigh approximately 3 billion tons. Or let's go another way, maybe something smaller like a sugar cube. A sugar cube of neutron star stuff would weigh as much as a mountain. And I'd be very strong. But what stuff makes up neutron stars? Why are they so dense? Well, their insides are a bit of a mystery. We know that they have atmospheres made up of hydrogen and helium, and an outer and inner core made from neutrons, electrons, and atomic nuclei. But we still don't know what hyperdense matter lies at their center. So, does this density cause a star's megamagnetism? Actually, we don't know. This takes us literally to the edge of scientific thinking. Scientists believe that as a neutron star is born, the magnetic field of the previous star shrinks. Combine this with this unusual, highly dense matter, and this could cause the phenomenal magnetism it wields. So we don't really know why a neutron star is so magnetic. It's a total mystery. But the neutron star's density is just the tip of the iceberg. They are capable of far stranger things.
We observe binary systems of 2 neutron stars that are in orbit around each other, and when we observe these systems, we see them getting closer and closer together all the time. So what will happen eventually is that they're going to collide. And when they merge, the neutron stars will be completely destroyed and form a black hole.
So when 2 neutron stars fuse together, colliding violently, this can create black holes. But this can also give birth to things called magnetars. And that's what is believed to have happened with our strongest magnet. However, there's another reason it's one of the rarest stars in existence. Not only was it once a magnetar, it's now what's known as an X-ray pulsar. This pulsar is truly incredible. It exists in a binary system with another star, orbiting each other. But it's not an equal relationship. The highly magnetic pulsar feeds off its lower density companion. With energy accumulating at its magnetic poles, it gives off bursts of X-ray pulses, like a lighthouse in the deep, dark corner of the universe. Dame Jocelyn Bell Burnell discovered them in 1967 and wrote the rule book for how we monitor these phenomena.
The pulses are short and quite steep, so these things have to be small. The other thing that we very quickly established was that the pulse period was very, very constant. It wasn't getting tired, which means it's got large reserves of energy, which means it's big. So it's small and it's big. You have to be more precise in what you're saying. It's small in width. It's big in mass. So high density. That's the first pulsar, CP1919. So that's what it sounds like if you listen to the radio signal. So that's a whole star spinning at that rate. And there are some that are even faster. If you listen to the fastest one, it would sound like your kitchen blender is going at 700 revs per second.
But we still don't know so many things about stars like the strongest magnet in the universe. Crucial elements of the mystery remain unsolved. Why are these stars so magnetic? And what is hidden deep in their core? Maybe one day, the star's secrets will be revealed.